Hello there. Today, we're going to dive into one of the most famous and difficult unsolved problems in all of mathematics. It's called the Riemann hypothesis. By the end of this video, you'll be able to understand the core concepts behind this conjecture. The Riemann hypothesis is a statement about the locations of the zeros of a special function called the Riemann zeta function. A zero is simply an input value for which the function's output is zero. Our main goal is to understand how this hypothesis connects to prime numbers. That's right, the Riemann hypothesis gives us a profound insight into the distribution of primes. It was first proposed by the brilliant German mathematician Bernhard Riemann in 1859, and it has stood as a challenge to mathematicians ever since. A $1 million prize awaits anyone who can prove or disprove it. To get there, we first need to build a few foundational concepts. Think of it like assembling the pieces of a puzzle. Let's get started. Okay, let's begin with the first puzzle piece, prime numbers. We've all seen them before, but let's quickly review them. So what exactly is a prime number? It's a whole number greater than 1 that can only be divided evenly by 1 and itself. Think of them as the fundamental building blocks of all other numbers through multiplication. Let's list a few examples to get us started. We have 2, 3, 7, 11, and so on. Notice that 4 is not prime because it's divisible by 2. 9 is not prime because it's divisible by 3. A key property that makes prime so important is the fundamental theorem of arithmetic. This states that every whole number greater than 1 is either a prime number itself, or it can be written as a unique product of prime numbers. It's like every number has its own unique prime DNA. Let's see this in action with a couple of examples. For the number 30, we can break it down into 2 times 15. Then 15 is 3 times 5, so the prime factorization of 30 is 2 times 3 times 5. There is no other way to multiply primes to get 30. How about 98? We can divide by 2 to get 49. And 49 is 7 times 7, so the prime factorization of 98 is 2 times 7 times 7, or 2 times 7 squared. So we've reviewed the definition and fundamental property of prime numbers. Keep in mind that while every number has this unique prime DNA, finding the prime factors of a very large number can be incredibly difficult. This property is the basis of modern encryption. The next piece of our puzzle is a very special function. It might look a little intimidating at first, but we'll break it down together. This is the Riemann zeta function. It's a function that takes a complex number is as its input. We'll talk more about complex numbers in a moment, but for now, you can just think of them as numbers that have both a real part and an imaginary part. The zeta function is initially defined as an infinite sum of fractions. It's the sum of 1 over n to the power of s, starting with n equals 1 and going to infinity. An infinite sum like this is called a series. And the key question about any series is whether it adds up to a finite number. This is called convergence. This series converges to a finite value only when the real part of s is greater than 1. So, for example, if s equals 2, we get a finite value. If s equals 0.5, the sum just grows infinitely large. But here's where things get interesting. Mathematicians use a technique called analytic continuation to define the zeta function for all complex numbers, not just those where the series converges. It's a bit like finding a hidden pattern and extending it. For our purposes, just know that the zeta function exists for every complex number except for one specific point. S equals 1. This special function is the star of our show. Now let's bring the first two puzzle pieces together: prime numbers and the zeta function. What's the connection? In a truly remarkable discovery, Leonhard Euler found a deep and beautiful identity linking the zeta function to prime numbers. This identity is at the heart of why the Riemann hypothesis is so important. It states that the infinite sum of 1 over n to the s, the zeta function, is exactly equal to an infinite product involving only prime numbers. It's the product of 1 over 1 minus p to the negative s for every single prime p. Let's expand the product part to make it clearer. It looks like this. First, take the term for the first prime, 2. It's 1 over 1 minus 2 to the negative s. Then you multiply that by the term for the next prime, 3, which is 1 over 1 minus 3 to the negative s. And you just keep multiplying all of these terms together, one for each prime. So what does this mean? It's saying that by knowing the value of the zeta function for a certain s, you can learn something about the product of all primes raised to that power. The zeta function acts like a bridge between the world of all natural numbers and the world of just the prime numbers. This formula connects the continuous world of complex functions to the discrete world of integers. It's a fundamental bridge that the Riemann hypothesis crosses. We've assembled the pieces, and now it's time for the big reveal. The Riemann hypothesis is a statement about the zeros of the zeta function. What is a zero? A zero of a function is any input value that makes the function equal to 0. In our case, it's a complex number such that zeta of s equals 0. The zeta function has two types of zeros. The first kind are called the trivial zeros. These zeros occur at the negative even integers, 2, 4, 6, and so on. They are called trivial because they are relatively easy to find and understand. They don't hold the key to the Riemann hypothesis. The other kind of zeros are the ones that fascinate mathematicians. These are the non-trivial zeros. Nobody has a simple formula to find them. Finding them requires extensive computation. It turns out that every single non-trivial zero found so far has a very specific structure. They all have a real part of 1/2. In other words, their complex number form is 1/2 plus some imaginary part. I times y. We can plot these zeros in the complex plane, which has a real axis and an imaginary axis. If we do this, all these zeros line up perfectly on a single vertical line. This line is called the critical line. The Riemann hypothesis is the conjecture that every single non-trivial zero of the zeta function lies on this critical line, which is defined by the equation x equals 1/2. So, let's recap. The hypothesis claims that all the secret non-trivial zeros of the zeta function are perfectly aligned on the critical line. It's a statement of perfect order hidden within what might seem like a random scatter. So why is this hypothesis so important? Its connection to prime numbers is incredibly deep. If the Riemann hypothesis is true, it would give us a powerful tool to understand how prime numbers are distributed. Let's be clear, the zeta function has no zeros on the critical line. If and only if primes are distributed in the most even and predictable way possible. If zeros exist on the line, it introduces a level of noise or randomness into the distribution of primes. It establishes a direct link between the location of the zeros of the zeta function and the errors in various approximations for the number of primes less than a given number. One such approximation comes from the prime number theorem. This theorem gives us a good estimate for the number of primes less than or equal to x, which is denoted as pi of x. The estimate is x divided by the natural logarithm of x. The estimate is pretty good, but it's not perfect. The error, the difference between the actual number of primes and this estimate, is related to the zeta function's zeros. Now let's look at a different, better approximation for pi of x, called the logarithmic integral lig. This approximation also has an error. If the Riemann hypothesis is true, it says something specific about how large that error can be. It gives us a bound, a maximum size for the error. Essentially, the closer the zeta zeros are to the critical line, the smaller and more well-behaved the error in approximating primes will be. So the hypothesis is like a key that unlocks a deep secret of number theory. It promises to tell us just how orderly or disorderly the sequence of prime numbers truly is. Let's explore this idea further with a worked example, connecting the Euler product formula to a specific number. Our goal in this scene is to demonstrate the Euler product formula for a simple case and see how it works. We'll use the case where the input to the zeta function is s equals 2. First, let's write out the zeta function for s equals 2. We're summing 1 over n squared, so we get 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. This is the sum of the reciprocals of the squares. Now let's look at the product side of the Euler formula for s equals 2. We need to multiply terms of the form 1 over 1 minus p to the negative 2 for every prime p. So we have 1 over 1 minus 2 to the negative 2 times 1 over 1 minus 3 to the negative 2, and so on. Since p to the negative 2 is the same as 1 over p squared, we can rewrite each term. The product becomes 1 over the fraction 1 minus 1 over p squared. Now we simplify. In the first term, 1 minus 1/4 is 3/4. In the second term, 1 minus 1/9 is 8/9. In the third term, 1 minus 125 is a 45, so we're multiplying the reciprocals of these fractions. This gives us a product of 4 3 times, 9 8 times, 25 4, and so on. The amazing part is that Euler proved that this infinite product is exactly equal to the infinite sum on the other side of the formula. In fact, he famously showed they both equal pi squared over 6. This example shows the power of Euler's formula. It connects a seemingly simple sum of fractions to a complex product of terms based on primes, demonstrating a deep relationship within number theory. Now, for our second worked example, let's explore the concept of a trivial zero and confirm that s equals 2 is indeed a zero of the zeta function. Our objective here is to show that a trivial zero satisfies the condition for being a zero. This will give us a concrete example of a zero that we can easily find without resorting to complex analysis. Remember, the definition of the zeta function as an infinite sum only works for complex numbers with a real part greater than 1. So we can't just plug in s equals 2 into the original series. If we did try, we would get the sum of 1 over n to the power of 2, which is just the sum of n squared. 1 squared plus 2 squared plus 3 squared, and so on. This sum clearly diverges to infinity, so this method won't work. Instead, we must use the extended definition of the zeta function, often given by a formula called the functional equation. This functional equation, discovered by Riemann himself, relates the value of the zeta function at s to its value at 1 minus s. This formula is valid for all values of s where zetas and zeta 1s are defined. Let's plug in s equals 2 and see what happens. We substitute 2 for s. Notice the term sin ps over 2. This is the key. The argument of the sin a function becomes minus pi. And the sin a of any integer multiple of p is 0. That's a fundamental property of the sin a function. Since one of the factors on the right-hand side is 0, the entire expression becomes 0. Therefore, zeta of negative 2 equals 0. We have successfully verified that Sachi R2 is indeed a zero of the zeta function. This method works for all negative even integers. The sin term will always be 0, making the entire expression 0. This is why they are called trivial. Their zeros are straightforward to demonstrate using the functional equation. For our third and final worked example, let's explore the concept of the critical line and a non-trivial zero. Our objective is to plot a non-trivial zero and the critical line in the complex plane to visualize the core of the Riemann hypothesis. This will help make the abstract idea of the hypothesis more concrete. First, let's draw the complex plane. It has a horizontal real axis and a vertical imaginary axis. We can plot the trivial zeros we just discussed on the real axis at Saj 2, 4, 6, and so on. But these aren't the zeros we're interested in for the hypothesis. Now let's draw the critical line. This is the vertical line at a real part of Ontaasas. The Riemann hypothesis claims that all the important zeros must lie on this line. Now, let's find a non-trivial zero. Remember, these are difficult to find, but we can look one up. The smallest non-trivial zero is approximately at s equals 1/2 plus 14.1347 times I. Here, 14.1347 is the imaginary part, and it is a known value that has been computed to high precision. How would we plot this? The real part tells us our horizontal position, and the imaginary part tells us our vertical position. Since the real part is exactly 1/2, the point S1 must fall directly on the critical line we just drew. The imaginary part of 14.1347 tells us to go up the imaginary axis to that value. And there it is, perfectly on the line. Because the zeta function is symmetric with respect to the real axis, if S1 is a 0, then its complex conjugate, S1 bar, must also be a 0. So we also have a 0 at 1/2 minus 14.1347i also on the critical line. Now let's add the next few non-trivial zeros. As you can see, every single one of them lies on this same critical line. The Riemann hypothesis is the assertion that this pattern holds forever for all infinitely many non-trivial zeros. Let's summarize everything we've learned. The Riemann hypothesis proposes a deep connection between a complex function, the Riemann zeta function, and the distribution of prime numbers. We started with prime numbers, the building blocks of arithmetic, and the Euler product formula, which is a bridge between these primes and the zeta function. We saw that the zeta function has two types of zeros, the predictable trivial zeros on the negative real axis, and the mysterious non-trivial zeros that lie somewhere else in the complex plane. The hypothesis is a statement about these mysterious non-trivial zeros. It conjectures that every single one of them lies on the critical line, which is the line in the complex plane where the real part is exactly 1/2. Why is this so important? Because the truth of this conjecture directly impacts our understanding of the distribution of prime numbers. A proof of the Riemann hypothesis would unlock secrets that have puzzled mathematicians for centuries, confirming a hidden order in the primes. No one has been able to prove or disprove it yet, despite hundreds of years of effort. It remains one of the ultimate challenges in mathematics, a testament to the enduring mystery and beauty of numbers. To help solidify these ideas, let's try a few practice questions. Take your time to think about them before I reveal the answers. First question. Which of the following is a prime number? A, 1, B, 2, C, 4, D, 9. Pause the video and consider your choice. All right, let's look at the answer. The correct answer is B, 2. Remember the definition. A prime number must be greater than 1. So A, 1 is not prime. B, 2 is prime because it's only divisible by 1 and itself. C, 4 is not prime because it's divisible by 2. And D, 9 is not prime because it's divisible by 3. Second question. For which values of the complex numbers is the Riemann zeta function defined? Is it A, all complex numbers? B, only for S where the real part is greater than 1C, all complex numbers except S to 1? Or D, only for prime numbers? Ready for the answer? The correct answer is C, all complex numbers except S equals 1. The original infinite sum definition from the Euler product only converges for a real part of S greater than 1. However, through a process called analytic continuation, the function is extended to be defined for all other complex numbers, with the exception of a singularity at S equals 1. Final question. The Riemann hypothesis states that all non-trivial zeros of the zeta function lie on which line in the complex plane? Is it A, the real axis? B, the imaginary axis? C, the line Ries point 1, or D, the line Ries 2? The answer is D, the line Ries equals 1/2. The hypothesis is specifically about the non-trivial zeros, which are complex numbers. It states they all lie on the vertical line where the real part is 1/2, known as the critical line. I hope these questions helped clarify the key points of our discussion. Thank you for joining me on this journey into the fascinating world of the Riemann hypothesis. I know we've covered some advanced topics, but I hope you now have a clearer understanding of what this famous problem is all about. We've learned about the connection between primes and the zeta function, and the central role the critical line plays in this mathematical drama. The Riemann hypothesis is a beautiful example of how seemingly abstract mathematical ideas can hold the key to understanding the fundamental structure of our number system. Whether you're a budding mathematician or just curious, this problem stands as a testament to the enduring quest for knowledge and the beauty of the unsolved. Who knows? Perhaps the person who finally cracks it will be watching this video right now. Thanks again, and keep exploring.